Alright, welcome back. This is going to be the second video now that has to do with the Eisenman Memorial. In the first video we went ahead and set up the grid, and then we went ahead and removed or culled any grid points that were outside of our site boundary curve, and that's what you're seeing on my screen here. Two quick things I want to note. Notice that when I started to label this, I actually called this step 00. Remember in Grasshopper we always start counting at 0, so it's in a good habit just to start doing that, so I'm going to refer to this as step 00. The second thing we want to do is we're going to go ahead and start the next phase here. And to do that, what we need to do is find the closest point on the ground surface, import the attractor points and attractor curves, and then find the minimum distance between the surface closest points and the attractor points. So we'll talk through all that here in just a moment. One thing we know we're going to need is all those grid points that we had in the last step up above here, this culled points. And if you remember, anytime we want to bring something down below, this is my paragraph right here. If I want to start grouping things, I could group all of these together, and I could group all of this together because this is all about how to create that pattern. And then last but not least is the actual cull operation there. If you remember, this is my first paragraph, and to bring information down below, I like to do that with a wireless receiver. So the first thing you need to do is have a container. Those containers are found in this parameters tab within here. Then we need to know what type of geometry do we have here. If we hover over this L output, or put a panel tool in there to visualize it to see what we have, we know that what we have is a series of points, X, Y, Z values that represent all of these points. So we're going to need one of those point containers. Find that underneath parameters, geometry, and point. I'm going to wire that in. I'm going to relabel this to call this my culled grid points. Okay. I'm going to go ahead and set the wire display. Oh, let me bring this over a little bit so you guys can see it. Wire display and hidden like so. Now I get that little Wi-Fi receiver, and when I click on it I can see where it's coming from. Now that the data has been transferred, I can turn off this older component like so and bring this one down below here. There it is. So let's go ahead and start to import. We'll skip this first step for a moment. We'll import the attractor points and the attractor curves. Right now I've got two of them in here. Let's turn this off for just a moment. You can see them in green here. I'm also going to go ahead and turn off in Rhino my aerial view because we don't need that right now. And I want to bring in these two objects, the attractor points as well as this one attractor curve. To do that, we're going to use again a point container. So go to parameters, geometry, and point. And I'm actually going to make two of these, so copy paste them. I'm going to label one attractor point 0 because again we want to get in the habit of start counting with 0. And the second one attractor point 1 and ATT point. And let's update this one as well. There we go. And then we're going to go ahead and bring in a curve component. So again, parameters, geometry, and curve. And attractor point or attractor curve 0. And all you're going to do is right click and set one point for each of these objects. Set one. So. And set one. There we go. Okay, so now if you remember what we did with the attractor point definition with the circles is we had to measure the distance from all of the grid points to each of the attractor objects here. So to do that, we're going to go to vector, point, and distance component. And we're going to measure the distance from the grid points to attractor point object 1. I'm going to copy paste that. We're going to also measure the distance from the grid point to attractor point 1 right there. Excuse me, the first one was 0, the second one was 1. And then we can't do it with a curve because the distance component was using points to measure it by. So we use the curve closest point component. So we went to curve, analysis, and curve closest point, or curve CP. The points go into the P input, so all of our grid points, and the curve goes into the C. And as a result, we get the distances and all those points that are mapped along there. So what you're doing, I'm going to turn these points back on, like so. You're measuring from all of the green grid points to each attractor object, including this attractor curve, like so. All right. So there, we've gone ahead and measured them. Now we need to find the minimum distance between them, and this is where that kind of round robin thing happens. So what we want to do is find the minimum distance between the first two objects. So we're going to go to Math, Utility, and Minimum. And we're going to compare minimum of object 1 to attractor point 2, like so. And we're going to compare the result of that, this round robin thing, to the curve CP, the distances coming from here, the D coming from there. So we compared the distances between the first two attractor objects, the first two attractor points, and found the result of that. And then we compared that result to the curve closest point. Again, this is all a repeat of what we just did in class on this past Friday, but just here it is again for clarification. Now, we've gone ahead and found the minimum distance between there. We got to go back and find this ground CP. What that means exactly is I'm going to go ahead and turn off my attractor objects. I'm going to turn everything off except for my culled grid. Preview off, like so. The reason that this is important is because if you go to a perspective view, and this will actually work really well, is you'll notice that the actual ground surface undulates, okay? And while the ground surface undulates, our grid points are on the XY plane, basically kind of floating in space there. We want to get we want to map all of these floating grid points down onto this undulating ground plane, okay? We don't want them to all be flat on the XY, we want them to actually reside on this ground plane. So the same way that the curve closest point maps a corresponding point along a given curve. So remember how each of these grid points gets assigned to a perpendicular line, a tangent line to this selected curve. We can do something very similar but do it with a surface. It's called surface closest point, or surface CP. So what we need to do is give ourselves a little bit of room here. We need to reference in the boundary, the site surface here. So again, go to Parameters, Geometry, and we can bring it in as a surface, or what I like to use is a BREP, is a boundary representation. It's a very generic container for objects that have boundaries. That's surfaces, polysurfaces, things along that lines, okay? So instead of using a true surface component, which we could use, I like to use BREP just because it's more generic and more universal. So I'm going to drop in the BREP component. I'm going to relabel this as my ground surface. And I'm going to set one BREP. Because it's already selected here in Rhino, you'll see it just flicker. And you know it's gone gray within there. So if an object's pre-selected and you right-click set one, it'll flicker for a moment. If you don't, or if you did it wrong, you can always clear out an entry. Just right-click, go to Clear Values. This component goes back to being orange. Right-click, set one BREP, and go ahead and click on the surface right there in Rhino. And there it is. Okay, so now that we're analyzing a surface, figuring out how these points get mapped onto a surface, we're going to go to our Surface tab in the Analyze panel. In the same way we have a curve closest point, we have a surface closest point, or BREP. We're going to use the Surface CP. The points that we want to test are all of our grid points. The surface we want to test against is our ground surface. So let's go ahead and wire the ground surface into there, and let's wire the grid points into the P input. And now what you'll see is you get a grid of points that are projected down onto this undulating plane. Now there will be a slight issue with this, and I'll explain this a little bit later, but we'll come back to it in a moment. Now what we want to do is we want to use the result, these new points, not the original grid points that are up in space, but these newly projected points to measure all of our distances. So we can just rewire where all of these grid points we're going to with this new set of points. And we can turn these off for a moment. And I'm going to turn off my curve closest point. And there it is. So now what we've done is we've taken the grid points. We've found the closest point on the grid surface. We've imported all of our attractor objects. And we found the minimum distance between those attractor objects and the ground, the grid of points. What I'm going to do is I'm going to go ahead and start grouping some of this stuff together just for organizational purposes, like so and like so. And I want to talk, let's try that again. Group. There we go. And I want to talk a little bit about why, what this is doing and why this isn't the best result, but we'll come back and edit that a little bit later. This works really well for us. So what's happening is that in the same way that when we use the curve closest point, it maps a line that's tangent to our source object, the curve or the surface. The same thing's happening here in the surface closest point, is that this point here up in space, which is part of our grid point collection right there, is being projected down in the closest distance onto this, meaning that if I put a sphere around this point, it would be tangent to this surface at that exact location. Okay. Again, the same way that that is kind of corrected, we get a little bit of offsetting happening. So if I go to a true top view and I look here, you'll see that the green ones, which are my original grid, and the red ones, which are my projected or my surface CP grid, don't always align perfectly. They're kind of skewed off, and depending upon the undulation of the surface, they get skewed in slightly different directions. So this isn't a true extrusion in a true vertical axis. It's more of a projection that is perpendicular to the surface, which means that the resulting grid is a little askew. It's okay, it really is not playing a real big role, and we'll also have an option later on to go ahead and figure out a different way to do this without that distortion happening. For now, this will work. We've now completed this second step, and we just have to make the stellas and make them have the proper heights. We'll talk about that in the next step.